Welcome to the video on side-side-side similarity. The purpose of this video is to introduce you to the side-side-side similarity theorem and its use in proofwriting. First of all, let's take a look at what it says. This theorem says that if the lengths of all three pairs of corresponding sides of two triangles are in proportion, then it follows that the two triangles are similar to each other. All right, so let's go see how we would use this in a proof. Our first example gives us a couple triangles with the given lengths, and they very nicely labeled these lengths in the triangles for us, and they want us to prove that the two triangles are similar. Now, if we were to try to use one of the methods that we've learned in the past, either angle-angle similarity or side-angle-side similarity, neither one of those would work because we don't have any pairs of congruent angles, and nor do we have any way of getting pairs of congruent angles in this problem. So we have to go and rely on the side-side-side similarity theorem. All right, so we're going to go ahead and we're going to get started and work with the givens. What this theorem is saying, it's saying if we take and compare any two corresponding sides, so if we were to take the shortest two corresponding sides in each triangle and compare them 2 to 1, that's the same as what we get when we compare the medium-sized sides in each triangle, which is the same as the ratio that we get when we compare the longest pair of sides in each triangle. All right, so let's go ahead and take a look at what that would look like here in our proof. We're going to start out by stating the givens. And then what we're going to do is we're going to take those given sides and we're going to write them such that they're in proportion. I'm going to compare smallest to smallest, medium to medium, and longest to longest. So when I compare the smallest pairs of sides, I'm comparing AC to DF. Remember, a ratio is just a comparison between two numbers. I can compare anything I want to. I'm going to compare the medium-sized sides. So that comparison ends up being 4 to 2, but when simplified is really just 2 to 1. And then lastly, I'm going to go ahead and I'm going to compare the longest pairs of sides. And that ratio too, when I simplify it, is really just 2 to 1. Since all I did was substitute in side lengths for the sides, I'm going to call that step substitution. And if I look at these ratios that I got when I compared the corresponding side lengths, I find that each and every one of these ratios is 2 to 1. And since their ratios are all the same, it's fair now to go ahead and to say the lengths of the corresponding sides are in proportion. I'm going to go ahead and say that the ratio between AC and DF is exactly the same as the ratio between side AB and side DE, which is exactly the same as the ratio between side BE and side EF. And that's because anytime I have ratios that are the same, my corresponding sides are in proportion. And since all three pairs of corresponding sides are in proportion now, I'm all set to go ahead and to say that those two triangles are similar. So lastly, I can conclude that triangle ABC is similar to triangle DEF. And the reason for that, side-side-side similarity. Now, if at this point you feel like you understand the second example is very similar to the first, you're all set to go ahead and shut the video off. But if you'd like to see another example of how this works, go ahead and flip the paper up to the top of the back side. So this question is very similar to the first, except whereas in the first one the picture was already labeled for us, this one we have to go ahead and label the diagram. So I'm going to go ahead and take those side lengths that they give us in the givens and go ahead and label the picture. So AC was 8. I guess I mislabeled AB there, so I'm going to go ahead and fix that. And really, again, the only thing that I need to be careful of here is that when I go ahead and compare corresponding sides, I want to make sure that I compare the longest side in each triangle. I want to make sure I compare the middle sides in each triangle. And I want to compare the shortest side of the first triangle to the shortest side of the second triangle so that I'm consistent when I write my ratios. Like the first proof, I'm going to go ahead and I'm going to get started with the givens. Maybe this time, just to be different, I'll write my proof in a 2-column format. So again, all I'm doing here is stating the given. And then I'm going to go ahead and I'm going to write my ratios. Remember, a ratio is just a comparison between any two things that we want to compare. And in this particular case, we want to compare longest side to longest side, shortest side to shortest side, and medium side to medium side. Twelve to 9, when I simplify or reduce, these will both divide by 3. Next, I'm going to go compare the middle sides. These numbers will both divide by 2. And then lastly, I'm going to compare the shortest sides. And that's just simple substitution. And now I'm noticing that after I do these comparisons, all 3 of these ratios are exactly the same. And therefore, it must follow that my side lengths must be proportional. So that's going to be my next step, is to go ahead and write that extended proportion. And that's just because when things have the same ratio, we say that they're in proportion. I'm going to cite statement 2. I should have up here cited statement 1 for my substitution. And now that I've shown that all 3 pairs of sides are proportional, it's fair to go ahead and say that those 2 triangles are similar. So ABC and CDE. And the reason for that is that new theorem that we learned today, side, side, side similarity. So at this point, if you have questions or concerns, please drop them down at the bottom of your paper, or feel free to shoot me an email and we'll talk about them when you come back to class. And the next time you come back to class, be ready to practice some of these side, side, side similarity proofs.